Hello everyone, my name is Guoxi and I'm from Clemson University. Today I'm going to present our paper, A Task Parallel Approach for Localized Topological Data Structures. Here is the outline of my today's talk. First I'll give an introduction on the topics, and then I will talk about the previous work and our proposed approach. Next I'll talk about results and some future work. It is pretty common nowadays that unstructured meshes are getting very large. For example, the standard dataset on the left side has 17 million vertices and 100 million tetrahedra. The NASA Mass Lander dataset on the right side contains 143 million vertices and 789 million elements. The topological algorithms are supposed to run on these unstructured meshes and extract topological features. For example, the scalar field grid points, precision diagram or precision curve, more small complex, and so on. Typically, topological data structure is built for these topological algorithms. It encodes the mesh data, the vertices, edges, triangles, tetrahedra, etc. And it means to handle the topological relations, for example, the boundary relations, co-boundary relations, and adjacency relations. It is trivial for a regular dataset as vertices are distributed on the regular grid, but it is more complicated for a regular dataset. Some dynamic data structures have been proposed to solve the issue of running topological algorithms on large unstructured meshes. They decompose the mesh into multiple blocks, for example, the octopus cat dataset on the right side. They compute the topological relations upon request and discard these relations when no longer needed. Examples include the PR stock tree proposed by VIS et al., style tree proposed by Flagella et al., and tuple cluster proposed by Liu et al. However, such on-the-fly computation of dynamic data structures can be very slow when you compare it to the data structures that initialize all the topological relations. For example, it is 2 times slower in average when extracting scalar field grid points, and 4 times slower when computing more small complex. Why is that? Here we show the classic pipeline of dynamic data structures. They compute connectivity information on demand. In such case, we compute the block 1 and use the relations of block 1. And next, when we move to block 2, we compute relations of block 2 and discard the relations of block 1, and so on and so forth. Modern computer systems are equipped with multi-core CPUs, so the question here is, can we utilize this multi-threading feature to improve the pipeline? Our answer to this question is yes. So in our proposed approach, we separate the computation of topological relations from the algorithm execution. That is, we have another thread that will pre-compute relations for the thread that executes the algorithms. So in here, thread T2 will always pre-compute the relations for thread T1. And we call our data structure with such pre-computation mechanism accelerated cluster topological data structure, aka ACTOPL. In ACTOPL, we have used the producer-consumer prototype for the pre-computation mechanism, and we further divided producer into leader producer and worker producer. The consumer thread is the one that is responsible for running topological algorithm. It spawns the leader producer and sends the request to the leader producer. The leader producer, on the other hand, will spawn the worker producer. It also acts like a middle layer between the other two rows. It will compute the topological relations immediately once it receives the request from the consumer, and it will also notify the worker threads for pre-computation. Worker producer is pretty simple. It basically just computes the topological relations for different blocks and changes the working block when it is notified by the leader producer. So how does the worker producer handle the pre-computation? There are two different things I need to decide for pre-computation. One is the moving direction. The work producer can pre-compute the blocks following the sequential order, or it can move to the neighboring blocks of the current blocks. The other one is the number of topological relations it needs to pre-compute. First, it can compute only one single relation, or it can compute multiple topological relations at the same time. Combining these options together, we have 4 different choices in total. Before we move to the actual results, let's look at the experimental setup first. We test our data structures on a Linux machine with TTK version 1.0. The machine is equipped with Intel Core i7 CPU and 32GB RAM. We test our data structure with many different topological algorithms. The first one is just to extract different topological relations from the mesh. The second one is to extract the critical points, such as minima, maxima, saddles, based on the scattered field value. And the next one is to compute the formal gradient on the mesh and also the Mossman complex. We compare our data structure with TTK built-in data structures. The TTK explicit triangulation is the studied data structure that computes topological relations before the algorithm execution, and TTK compact triangulation is an implementation of the dynamic data structure topocluster. We have run our experiments on 8 different datasets. The number of vertices ranges from almost 1 million to 70 million, and the number of tetrahedra ranges from 5 million to almost 100 million. Let's first look at the plugin that is easy to pre-compute for work producer. Here we choose the discrete gradient, which loops the vertices in a sequential order. The result shows that October is 1.8 times as faster as compact triangulation. It is also only 10% slower than the explicit triangulation. Regarding the memory usage, October only uses 15% more memory than the compact triangulation, but it is 2 times as compact as the explicit triangulation. When it comes to the plugin that is harder for the work producer to pre-compute, for example, Mossman complex plugin, here, even though it is 2.6 times as slow as explicit triangulation, it is up to 8.5 times as fast as compact triangulation, while in average it is 3.4 times. Regarding the memory usage, October only uses 6% more memory than compact triangulation, but it is 1.8 times as compact as explicit triangulation. As we all know, some topological algorithms can be implemented in parallel. For example, using data parallel technique, which divided data into small pieces and it can be processed by multiple threads. Dynamic data structures are very suitable for such technique as it already decomposes the data into different blocks. As we mentioned earlier, consumer thread in October is responsible to execute the algorithm. So in our data structure, it simply generalized the producer-consumer association. For example, if you have 4 consumer threads who run the algorithm execution, it will duplicate the corresponding lead producer and the worker producer. Here we show the results of running parallel discrete gradient algorithm with different data structures. For the time chart, the bottom bar shows the time for preprocessing, and the top bar shows the time for algorithm execution. As we can see, dynamic data structure spends less time on preprocessing, but more time on algorithm execution. Overall, October is both the fastest and the most compact data structure compared with the other two. It is 1.2 times as fast as compact triangulation, and even 1.6 times as fast as explicit triangulation. It uses 8% less memory than compact triangulation, and it is also 2 times as compact as explicit triangulation. The current limitation of VIC-topo is that some algorithms may exhibit complicated traversal pattern. That is, the moving direction is not linear, and different topological relations will be needed at different steps. One possible direction would be to use some learning-based methods to further guide the pre-computation of worker producer, or we can apply such task parallel approach on specific topological algorithm. We can also explore other heterogeneous parallel architectures for potential improvement. And that's all for my presentation. Thank you for listening. Have a great day.